If you look back at the early 20th century, physics was facing a total crisis. According to classical electromagnetism, the hydrogen atom shouldn't even exist. An electron orbiting a nucleus is accelerating, and Maxwell's equations tell us that any accelerating charge must radiate energy. If it's constantly losing energy, that electron should spiral into the nucleus in a tiny fraction of a second. Matter should just collapse. But today, we're diving into a paper from 1987 by H.E. Puthoff that suggests a wild alternative. It's titled Ground State of Hydrogen as a Zero-Point Fluctuation Determined State. And it argues that the reason the atom doesn't collapse isn't just because of some abstract quantum rule, but because of a literal physical ocean of energy we're all swimming in.
It's a fascinating perspective because it shifts the focus from the atom as an isolated unit to the atom as a part of a dynamic system with the vacuum itself. Puthoff uses a framework called stochastic electrodynamics, or SED. In SED, you don't start with the usual quantum mechanical wave functions. Instead, you assume the vacuum is filled with real, classical, random electromagnetic waves. These are the zero-point fluctuations, or ZPF. The core idea Puthoff explores is that the ground state of the hydrogen atom, the lowest energy level where the electron sits, is actually a state of dynamic equilibrium. The electron is indeed radiating energy away as it orbits, just as classical physics predicts, but it's simultaneously absorbing an equal amount of energy from this background zero-point field. It's like a boat on a stormy sea. It's being tossed around and losing energy to friction, but the waves are constantly pushing energy back into it.
That analogy of a boat on a stormy sea is helpful, but the math behind it has to be incredibly precise to keep the electron in a stable orbit. Puthoff isn't just saying maybe this happens, he's trying to show that the numbers match exactly what we see in the Bohr model of the atom. Specifically, he's looking at that ground state radius. In the Bohr theory, the angular momentum is quantized, leading to that specific radius where the electron stays. Puthoff wants to derive that same result using only classical mechanics and the zero-point field.
Exactly, and to do that, he starts by modeling the electron's motion as a one-dimensional charged harmonic oscillator. He places this oscillator in that random background of zero-point radiation. He uses an equation of motion that includes radiation damping. That's the energy the electron loses and the force from the zero-point electric field. By solving this, he calculates the average power the oscillator absorbs from the background. One of the really elegant parts of this derivation is how he handles the spectrum of the zero-point field. As established by earlier researchers like Timothy Boyer and Trevor Marshall, the energy density of these fluctuations has a cubic dependence on frequency. This isn't just an arbitrary choice. It's the only spectrum that stays the same regardless of how fast you're moving through it, which we call Lorentz invariance.
So he calculates the power absorbed by a one-dimensional oscillator, but an electron in a circular orbit is moving in two dimensions. How does he bridge that gap?
He makes a clever observation using the Bohr model's geometry. A circular orbit can be viewed as two one-dimensional oscillators working together in a plane, but oscillating out of phase, what physicists call being in quadrature. If you have an X oscillation and a Y oscillation timed just right, you get a circle. Because of this, the power absorbed by the electron in its circular orbit is exactly double what he calculated for the single one-dimensional case. He winds up with a specific formula for the absorbed power that depends on the electron's charge, its mass, the orbital frequency, and Planck's constant, though in SED, Planck's constant is viewed more as a scale factor for the field's strength, rather than a mysterious quantum integer.
Okay, so he has the energy in from the vacuum. Now he needs the energy out from the orbital acceleration. Classical physics already has a standard formula for that, right?
Yes, the Larmor formula. It tells us the power radiated by an accelerating charge. For an electron in a circular orbit with a specific radius and frequency, the power radiated is proportional to the square of the acceleration. Puthoff sets these two equal to each other. The power absorbed from the ZPF equals the power radiated away. When he does the algebra to find the point where these two balance out, he gets a stunning result. The equilibrium condition simplifies perfectly to the exact formula for the Bohr radius. Specifically, he finds that the angular momentum equals h bar. It's a direct, quantitative match with the standard quantum result, but derived entirely through classical interactions with a background field.
It's almost hard to wrap your head around because we're so used to being told that the Bohr model was a failed or transitional theory that required non-classical quantum jumps to make sense. But Puthoff is suggesting the physics was there all along, we just forgot to account for the background radiation. This isn't the only place where this kind of thing happens, though. He mentions the Casimir effect and van der Waals forces. How do those fit into this picture?
Those are the success stories of the SED approach. The Casimir effect is that famous phenomenon where two uncharged metal plates in a vacuum actually attract each other. In the quantum view, it's because the plates limit the types of virtual particles that can pop in and out between them, creating a pressure difference. In the SED view, it's because the plates act as boundaries for the classical zero-point waves. Certain wavelengths can't fit between the plates, so there's more radiation pressure pushing them together from the outside than pushing them apart from the inside. Van der Waals forces, which keep molecules sticking together, can be explained the same way, as interactions mediated by these background fluctuations. By adding the hydrogen atom to this list, Puthoff is arguing that the ZPF isn't just some niche effect for plates or molecules, but the literal foundation for the stability of all matter.
I want to push back on that for a second. If SED is so successful at explaining the hydrogen ground state and the Casimir effect, why isn't it the standard way we teach physics? Why did quantum electrodynamics, or QED, become the dominant theory instead? There must be a catch or a limit to how far this classical waves approach can go.
That's the big question. Puthoff himself acknowledges this in the paper. He points out that while SED works brilliantly for linear systems, like these harmonic oscillators, it struggles with nonlinear systems. The hydrogen atom is actually quite complex because the force between the electron and the proton follows the inverse square law, which is nonlinear. Puthoff's derivation here uses the Bohr theory's circular orbit as a simplification. He notes that moving from this circular model to the more complex, spherically symmetric ground state described by Schrödinger's equation is a much tougher mathematical nut to crack. In QED, the math is incredibly robust and handles these complexities through operator algebra and probability waves, which, while less intuitive, provide a more universal toolkit.
So is SED just a mathematical coincidence? Like it just happens to give the same answer for the simple cases?
Puthoff argues it's deeper than that. He notes that in many cases, the Heisenberg equations of motion in QED are formally identical to the classical equations used in SED. When you perform ensemble averaging in both theories, you often land on the same result. The real tension is philosophical. QED says the vacuum is empty and particles have intrinsic, mysterious quantum properties. SED says particles are classical, but the vacuum is a chaotic, energy-rich medium that drives those quantum behaviors. It's the difference between saying a person is inherently jumpy versus saying they are standing on a vibrating floor. Puthoff is very much in the vibrating floor camp. He even references Edward Nelson's work on stochastic mechanics, which tries to derive the Schrödinger equation itself from the idea of particles undergoing Brownian motion due to some background field.
That's a powerful shift in perspective. If the stability of the atom is a dynamic balance, it implies that matter is essentially fed by the vacuum. If you could somehow shield an atom from those zero-point fluctuations, if you could turn off the stormy sea, would the atom just collapse? Would the electron finally spiral into the nucleus like those 19th century physicists feared? According to this theory, yes, the collapse of the atom is only prevented by the presence of these fluctuations. It changes our definition of empty space from a void to a stabilizer. It also touches on the fine structure constant. Puthoff mentions that for SED to work, you need to be able to construct a constant with the dimensions of action from the theory's basic ingredients. The fine structure constant, which involves the charge of the electron, the speed of light, and the permittivity of free space, fits that bill. It suggests that the very constants of nature might be tied to how matter interacts with this background field.
It's also interesting that he brings up the work of Peter Maloney. Maloney argued that you could look at these effects through the lens of radiation reaction instead of zero-point fields, basically the particle's own radiation affecting itself. Puthoff points out that these two views, ZPF and radiation reaction, might just be two sides of the same coin, linked by something called the fluctuation dissipation theorem. It's a bit like debating whether a boat moves because of the waves hitting it or because of how the boat displaces the water. They're inextricably linked processes.
That's a key point. It suggests that whether we use the language of QPF or the language of quantum mechanics, we're describing a fundamental reciprocity between matter and the space it occupies. Puthoff's paper is really a call to take the physical reality of the vacuum seriously. He's trying to provide a pedagogical insight, as he calls it, to show that the ground state of hydrogen isn't just a postulate we have to accept, but a state that emerges naturally from the laws of physics if we include the vacuum in the equation.
And the implications of that are huge. If the vacuum is this active participant in the structure of matter, it opens up questions about whether we could ever tap into that energy or if it's forever locked in this equilibrium. While the paper stays strictly within the realm of theoretical derivation, the underlying message is that our world is much more interconnected and dynamic than a simple ball and stick model of the atom would suggest. We aren't just living in space, we are part of it, maintained by its constant invisible fluctuations.
It's a beautiful way to think about it. The stability of every single atom in your body is essentially a dance, a perfect balance between the energy it's shedding and the energy it's soaking up from the universe around it. Puthoff's work reminds us that even in the ground state, the lowest, quietest level of existence, there is a tremendous amount of activity happening just beneath the surface.
It really reframes the whole quantum versus classical debate. Instead of them being two different worlds with two different sets of rules, SED offers a bridge, suggesting that what we call quantum might just be what classical looks like when it's immersed in a zero-point field. It's a provocative idea that hasn't replaced QED, but it certainly offers a much more intuitive, physical picture of why the world doesn't just vanish into a puff of radiation.
And it reminds us that physics is never truly settled. Even a question as basic as, why does the hydrogen atom stay together, can be revisited decades later with a new perspective that challenges our fundamental assumptions about the vacuum. It's about looking for the most parsimonious explanation, the one that uses the fewest magic rules and relies instead on the deep underlying symmetries of nature.
That's a great place to leave it. A universe that isn't just a collection of objects, but a vast, shimmering field of energy that holds everything in a delicate, perfect balance. It's a high-stakes equilibrium that we're all benefiting from every second of our lives.
Exactly. The next time you think of a vacuum as nothing, just remember it's the very thing keeping your atoms from collapsing.
In 1948, a Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratories in Eindhoven. He wasn't looking for the secrets of the universe. He was trying to understand why mayonnaise and paint are so thick. He was studying colloids, tiny particles suspended in a liquid, and he noticed something strange about how these particles clung together. At the time, the common explanation was the van der Waals force, a basic electromagnetic attraction. But something about the math wasn't quite right. When Casimir mentioned this puzzle to Niels Bohr, the father of the atomic model, Bohr gave him a cryptic piece of advice. He told Casimir that his problem had something to do with zero-point energy. That one hint changed the course of physics. It moved the focus away from the particles themselves and toward the nothing between them. To understand what Bohr meant, we have to throw away our classical intuition of a vacuum. We usually think of a vacuum as an empty box. Take out all the air, all the light, all the heat, and you're left with exactly zero. But in quantum field theory, nothing doesn't exist. Instead, space is filled with fields, like the electromagnetic field, which are never truly at rest. Think of the entire universe as being made of invisible, microscopic springs. Even at absolute zero, even in the darkest void, these springs are vibrating. This is the zero-point energy, the lowest possible energy state of a system. Because of the Heisenberg uncertainty principle, you can never have a state of perfect stillness. If the energy were exactly zero, you would know both the position and the momentum of the field precisely, which quantum mechanics forbids. So, the vacuum hums. It's a sea of virtual particles, photons, and other quanta that pop into existence and vanish in a fraction of a nanosecond. They are temporary, random energy fluctuations that collectively make up the fabric of reality.
Casimir took this abstract idea and imagined a simple physical test. He proposed placing two perfectly flat, uncharged metal plates in a complete vacuum, extremely close to each other. In his mind, he saw these plates acting like a set of filters for the vacuum's hum. Outside the plates, in the vast openness of space, vacuum fluctuations can happen at any wavelength. There's no limit to the size of the virtual particles that can appear. But inside the tiny gap between the plates, only certain wavelengths can fit. It's like a guitar string. If the plates are the ends of the string, you can only have vibrations that have nodes at the metal surfaces. Any fluctuation with a wavelength longer than the gap simply cannot exist there. Because there are more possible modes of vibration outside the plates than inside, there is a pressure imbalance. The vacuum on the outside is thicker with energy than the vacuum on the inside. This results in a tiny physical pressure that pushes the plates together. It's a force created by nothingness itself. For nearly 50 years, Casimir's prediction was a beautiful piece of theory, but it was almost impossible to prove. The force he was talking about is incredibly weak. To give you an idea, if you have two plates separated by a gap of 1 micrometer, that's 1/100th the width of a human hair, the pressure between them is roughly equivalent to the weight of a single grain of salt spread over a square meter. For decades, experiments were tried, but they were plagued by errors. If the plates weren't perfectly parallel, the measurement was ruined. If there was a tiny bit of static electricity or a speck of dust, the signal was lost. It wasn't until 1997 that the technology finally caught up to the theory. At Los Alamos National Laboratory, Stephen Lamoro used a torsion pendulum, a sensitive device that measures twisting force, to finally detect the pressure of the vacuum. He didn't use two flat plates because aligning them was too difficult. Instead, he used one flat plate and one spherical lens. This way, there was only one point of closest approach, eliminating the need for perfect parallelism. When he moved them to within 0.6 micrometers of each other, he felt it, a pull that matched Casimir's 1948 prediction to within 5%. Just a year later, in 1998, Omar Mohideen and Anushree Roy at the University of California, Riverside took it even further. They used an atomic force microscope, an instrument so precise it can feel individual atoms. They attached a tiny plastic sphere, only 200 micrometers wide, to a flexible cantilever. They coated both the sphere and a flat plate with a thin layer of aluminum and gold. As they brought the sphere closer to the plate in steps as small as 3 nanometers, they watched the cantilever bend. They were measuring forces on the scale of piconewtons, trillions of a newton. Their results were even more accurate, confirming the Casimir force to within 1%. This wasn't just a measurement, it was a demonstration that the vacuum is a physical substance with real mechanical properties. The nothing between the sphere and the plate was doing work, physically dragging the metal surfaces toward each other. This pressure from the void isn't just a laboratory curiosity. It's a fundamental limit for our technology. As we build smaller and smaller machines, the microelectromechanical systems, or MEMS, found in everything from smartphone sensors to medical implants, the Casimir effect can become a major obstacle. When gears and switches are shrunk down to the nanoscale, the vacuum pressure can become so strong that it causes the parts to stick together permanently, a phenomenon engineers call stiction. It's the ultimate irony of the modern age. As we master the very small, we find ourselves fighting against the energy of empty space. But some scientists see an opportunity here. If we can manipulate the shape and material of these surfaces, we might be able to create repulsive Casimir forces, allowing for frictionless bearings or even levitating nanomachines that float on a cushion of vacuum energy. The legacy of Hendrik Casimir's discovery goes far beyond mayonnaise or nanogears. It changes how we view the universe at its largest scales. If the vacuum has energy, then space itself has a weight. This vacuum energy density is the leading candidate for what we call dark energy, the mysterious force that is currently driving the expansion of the universe. When we look out at the distant galaxies flying away from us, we might be seeing the same pressure that pushed Lamoureux's plates together, just acting on a cosmic scale. Casimir died in 2000, shortly after his life's work was finally definitively proven. He lived long enough to see his name attached to a force that proved the vacuum isn't an absence, but a presence, a restless, vibrating foundation that everything else is built upon. Consider sharing this story with someone who wonders what lies at the heart of the void.